Next, in the combinational logic chapter, let's spend some time looking at the if statement. The if statement is much as you would expect it based on your programming experience so far. It just gives you the access to create more complex conditions. In this case, we've got an example of a simple robot-like controller. You can see that as input we have the distance of the robot from a nearby obstacle or wall and the distance where the robot should be, and the job of this controller is to move the robot forward or backward by telling an electric motor that moves the robot whether to go forward or backward and whether the motor should be on or off. So this makes for a great application for the if statement. As in the case statement, one of the really important things is to ensure that we define the initial values for all of our outputs so that no matter which case of our if statement, or in fact if nothing matches any of our if statements, we always consistently provide a defined output for every possible output that's given in this module. So in this example, we have two outputs. We have our job is to provide a value for both motor direction and motor enable. Therefore, before our if statement even runs, we'll go ahead and assign some value, an initial value to both of those. And then, of course, our if statement becomes rather straightforward. If our distance is greater than the goal, that means that we need to drive forward so we can get closer to the goal. So first of all, notice we use a begin followed by an end statement to allow us to put more than one line inside our if statement. And we simply set the motor direction to 1 so that the motor will drive forward, enabling us to go closer to the desired goal. And we turn the motors on as well. If the robot is less than the goal distance, that means it needs to drive backward, but the motors still need to be on. Of course, the third part that we haven't stated in our if statement is to assign a value when the distance is equal to the goal position. And in this case, our initial value handles that case. The most important part is we have disabled the motors. Given that the motors are disabled, we don't really care whether the motors are officially driving forward or driving backward, since obviously they don't move at all. So no big surprises here for the if statement, but again, be very, very sure to provide initial values for all the outputs that your if statement will assign to. You can see it assigned to both motor direction and enable here and here, and obviously that's what we need to cover. Let's take a look at some exercises to give you practice using the if statement. Here we have a similar sort of result. We're simply comparing two values, A and B, and then setting a result based on that comparison. If A is less than B, if A is greater than B, and implicitly if A is equal to B. Don't forget an initial value. An obvious initial value would be to set the result to 0, and then simply use an if statement to perform the appropriate comparisons and assign a value to result. Let's continue by looking at signed arithmetic. Now, an important thing to understand about signed arithmetic is that many operations, for example, when we add two numbers, subtract two numbers, decide whether two numbers are equal or not equal, don't care whether the values that are being operated on are signed or unsigned. However, some things, for example, multiplication, left shifts, those sort of things, are different in the case of unsigned versus signed numbers. A classic example is when we compare the number 1111 in binary to the number 0. If we're talking about unsigned numbers, of course, we would say that the number 15 is certainly greater than 0. However, if we're using a signed comparison, 1111 is the number -1. Obviously, -1 is less than 0. So, depending on the sign, it could be greater or lesser. So it's really important in Verilog to state the signedness of the numbers we're using. In this case, notice what our inputs are. We declare A and B as simply an input logic, a 6-bit number, and we don't mention whether it's signed or unsigned. By default, in Verilog, all values are unsigned. So therefore, A and B are treated as unsigned numbers. Our goal is to both perform a signed comparison. LT should be 1 if A is less than B from a signed perspective, and perform an unsigned comparison. The output is 1 if A is less than B using unsigned, and of course do equality. So to start with, let's look at how this implementation happens. All we're going to do is create internal signed variables, assign A and B to their signed equivalent, and then when we use this less than operator, because it's operating on two signed values, then our output result is using a signed comparison. Likewise, when we compute less than or equal to, less than unsigned, this works because both A and B are already unsigned values. So it's using two different pieces of hardware, one piece of hardware for a comparison of a unsigned value, and here a comparator that's designed specifically for signed operation. For equality, it doesn't matter whether the value is signed or unsigned. We could have compared either way because equality, again, doesn't depend on the signedness of that operation. All right, let's look at some exercises to give you some experience with using signed values in Verilog. So we'd like here to perform saturating arithmetic. Let's take a look back for a minute and talk about what saturating arithmetic is. And one helpful place to go is some earlier material that we have in the book. So if you'd follow me, we'll go look at our building blocks chapter and then the binary arithmetic subchapter. And there's a nice diagram here that shows how signed numbers operate. Now these are 4-bit signed numbers. Obviously in the problem we're looking at an 8-bit signed number, but this gives you a very good understanding of some of the challenges and our overall goals. If you notice, one of the important points in understanding signed arithmetic is this area right here. If you notice, what we've got is we have this signed arithmetic in a greenish color. We're tracking binary numbers here on the gray ring and translating that to their signed equivalent. So, for example, if we take the number plus 7, positive 7, and add 1 to it, an unfortunate thing happens. That positive 7 becomes the number negative 8. That's obviously a bad thing. So, in general, when we move across this line in either direction, here we're moving from positive to negative, then we get what's called an overflow. The sign suddenly flips and the answer we get is just completely wrong. So our goal for saturating arithmetic is to treat this red line as a barrier. In other words, what I'd like is for plus 7 plus 1 to still produce the value plus 7, because we can't represent the value plus 8. So let's spend a minute and then think through that a little bit. So we have the number 0111, which is equal to the number 7 in signed arithmetic, and we like to add 1 to that. Of course, I'm representing numbers in binary here, and I'm giving you their decimal equivalent over here. So we have 7 plus 1. And if we just do a standard addition, we would get the number 1000, which unfortunately, referring back to our diagram, is the number 8. 1000 corresponds to the number not positive 8, but negative 8. And obviously that result, taking 7 plus 1 and turning it into a negative 8, is really unfortunate. So in this case, we get what's called an overflow. An overflow is what happens when you take a positive number, add it to another positive number, and it produces a negative number, right? That's a bad thing. Likewise, if you have a negative number and add it to another negative number, we should always get a negative value. If we find that we get a positive value, that's obviously an error, and both these cases likewise are considered an overflow. Let's think about, first of all, how we detect overflow, and then how to correct overflow. Remember that the negative bit is the top bit of any number. Here in our 4-bit values, it's this bit 3 right here. So to put this in another form, if I look at bit 3, I'm going to call these numbers A and B. So let me just kind of space this out a little bit. We're adding A and B. So if you look at A bit 3, right, again, the way we number bits is starting at the top. 3, 2, 1, 0 is always our bottom bits. So of course bit 3 here is our top bit. That's the one that tells us whether we've got a negative bit. So if A3 is positive and B3 is positive, and our result, we'll call it for right now sum, is negative, so I'll put a tilde in front of that, then we know that we've got an overflow. Likewise, the negative case is fairly easy to detect. I've got this just backwards. This is the case where we added two negative numbers and got a positive number. Let me put that down here. Let's go back to the two positives to get a negative. We'll discuss the other case in just a moment. So obviously, trying one more time, if the top bit of A is 0, the top bit of B is 0, and the sum is a 1, something bad happened. So let me just state that one more time. If the top bit of A is a 0, and the top bit of B is a 0, and our resulting sum bit is a 1, then we have an overflow. And in fact, this overflow occurs when we have a positive number, right? The top bit was 0, indicating non-negative. We're adding it to a positive number. Here's our add to a positive number. And we see a 1 in our resulting sum. Then we've got an overflow. And here's what we'd like to do. We like to saturate the result. In other words, when we detect this case, then we want to saturate, or say that the maximum positive number should be the result. Then the corrected sum should be plus 7. Of course, this is for 4-bit numbers. Obviously, in the problem we're dealing with 8-bit numbers, so we'll talk about a larger value. But the sum should be plus 7. That's the largest positive number that we have. Likewise, if we have a negative number added to another negative number, let's take a quick example. We're going to have A, and we'll pick straight from our diagram here. We'll do negative 8 minus 1. So here's our negative 8, 1, 0, 0, 0. That's equal to negative 8. B is going to be the number negative 1, which is 1, 1, 1, 1. And again, this is an addition, so let me space things out a little bit here. Negative 8 plus negative 1. And if we just do our arithmetic directly, then of course we get this very unfortunate result. Which, if we again just follow the arithmetic, we're getting the value plus 7. Negative 8 minus 1 is a plus 7. And again, obviously we have this case where A3 is a 1, B3 is a 1, sum 3 is a 0. That's this case right here. And in this case, then our sum should be not plus 7 because we have an overflow in the opposite direction. We should like the sum to be minus 8. This is our smallest 4-bit signed value that we have, our most negative, So I'll call this the smallest negative number that we saturate to. So with all this, we have a fairly straightforward method of detecting overflow. We're going to look at these bits, the sum that's produced, and then we're going to produce a corrected sum. Now, a couple notes: when we move from 4-bit numbers to 8-bit numbers, those largest and smallest numbers go to plus 127 and minus 128, right? The numbers are a little bit different. And obviously, we would be looking at a bit 7 instead of bit 3, but the principles are very similar. Hopefully, this gives you the information to enable you to properly solve this problem. Essentially, compute a intermediate sum, check using an if statement for this first case, and if so, correct. Check using an if statement for the second case, if so, correct. Otherwise, the final sum doesn't need to be changed at all. Don't forget those initial values to specify and output our final sum, even if none of the if cases update that value. Let's look at our second signed arithmetic problem. Notice that in this problem, you need not just 1 bit, but you need to create a intermediate sum value that's 2 bits larger, a 9:0 value. And the problem gives an example where if you add these 3 8-bit numbers, we end up with a 10-bit result. So again, make sure you have 2 extra bits when you produce that sum, and then check both bits. Either one could be a 1 to indicate an overflow, and in that case, you need to saturate it. Notice that in this case, we put the explicit unsigned type to just make this problem really clear that we're doing unsigned arithmetic here, and you don't need to do any specific sign saturation. We're just doing unsigned things, but check both bits. I hope the material's been helpful. In our next lesson, we'll conclude by talking about complex conditionals.